Take a close look at the bedrock infrastructure of major Western cities. The subways, the tunnels, the bridges, these are aging systems built for a completely different era of human history. Above ground, millions of commuters spend hours every week trapped in gridlock, navigating road networks originally designed for horse-drawn carriages and mid-century population densities. While the West spends trillions trying to patch and maintain these rigid historical footprints, there is a lingering global assumption that China remains primarily an industrial hub, the world's factory floor. That assumption is decades out of date. They spent 40 years laying the foundation for a networked urban model, ignoring the industrial status quo. By bypassing the legacy footprints of the 20th century, this network is establishing a new technological standard for the modern city. To understand how they bypassed the West's infrastructure gridlock, you have to rewind 40 years. Outside of a few coastal enclaves, the vast majority of the country consisted of dirt roads, rudimentary transit, and extreme rural poverty. What followed was the largest and fastest human migration in recorded history. Hundreds of millions of people uprooted their lives, packing whatever they could carry, and moved from the countryside toward emerging municipal zones. Absorbing that sudden, staggering volume of human beings required an unprecedented scale of physical construction. They consumed more concrete in 3 years than the United States used in the entire 20th century. But this extreme starting point offered a rare, hidden asset. Urban planners avoided negotiating with legacy road layouts. They didn't drill through 100-year-old water mains or route around historic districts. Because there was virtually nothing to dismantle, they could implement interconnected, digital-first infrastructure directly into the fresh concrete. You can see the results of this blank slate approach most clearly in Beijing. We naturally think of capital cities as centers of political power, but Beijing functions primarily as a massive data processing hub. Instead of relying on static, timed traffic lights to manage congestion, over 12,000 distinct intersections are actively manipulated by centralized artificial intelligence that analyzes street flow second by second. The sheer volume of data generated by billions of daily metro passengers creates a continuous, high-resolution map of where human capital is moving. New physical architecture is purposely built to harvest this information. Terminals at Chongqing Airport are designed around automated flow, utilizing biometric scanning and facial recognition to track entry, exit, and transit times automatically. If we map out this digital ecosystem, this chart shows how it operates. Live traffic data and millions of camera feeds continuously stream down their respective spokes, converging straight into a unified processing center. Watch how the system reacts. If the AI detects an anomaly, a severe slowdown on surface streets, it sends instructions down this new spoke, automatically increasing the dispatch speeds of underground subway trains to absorb the stranded commuters. Add commercial transactions and security monitoring to the diagram, and the concept of isolated, independent city departments disappears completely into a single feedback loop. Beijing proves that modern concrete and steel are secondary. The city regulates itself like a software operating system. If Beijing processes the data, Shanghai executes the physical movement. It serves as the vascular system, pushing people and cargo through the economic machine. Here, extreme velocity has been normalized. Commuters ride magnetic levitation trains that cruise at hundreds of kilometers per hour as part of a routine commute. In many Western countries, high-speed rail is debated as a luxury or a highly specialized alternative. Chinese planners treat speed as baseline economic infrastructure. To maintain the necessary velocity, the human element is actively engineered out. Automated flatbeds carry freight with no cabins, no steering wheels, and no drivers, eliminating fatigue, shift changes, and manual errors. That philosophy reaches its peak at the global shipping hubs. Deep-water ports like Yangshan process tens of millions of standardized containers continuously. When an automated gantry crane shaves 80 milliseconds off the placement of a single container, that tiny efficiency scales across 40 million containers a year. Every minute saved in logistics, compounding over millions of interactions, directly dictates the nation's leverage in global trade. To ensure the hardware and software stay aligned, Shenzhen operates as the real-time research and development lab. This starts with the heavy infrastructure. Shenzhen retired its entire internal combustion fleet, deploying 16,000 fully electric buses to operate among the public. They do not run small, isolated pilot programs to test public reaction. They integrate unproven technologies directly into the daily routines of 20 million people simultaneously. Look at how consumer transactions work. Physical cash and credit cards have been aggressively phased out. Purchasing food or boarding a train requires only a biometric facial scan at a terminal. Erasing the physical friction of swiping a card or counting change accelerates local commerce. The financial metabolism of the city physically speeds up. These programs force human behavior to synchronize with the requirements of the new digital environment. The data processing of Beijing, the logistical speed of Shanghai, and the rapid adaptation of Shenzhen are not separate phenomena. They are integrated components of a single continental machine. While Western populations debate the funding needed to repair century-old tunnels, they are competing against a system that operates without legacy debt. This urban operating system exists as a finished product, designed for rapid replication. The digital nodes and transit networks that define these cities are beginning to appear along international trade routes as the model expands its footprint. For decades, international attention remained fixed on China's manufacturing output, overlooking the development of the predictive operating system that actually runs these centers. The defining feature of this system is a shift in materials. Planners have moved beyond relying exclusively on physical concrete, integrating invisible data networks directly into the civic foundation. The city operates as a single, synchronized machine where individual components communicate and respond collectively rather than acting in isolation. Understanding this mechanism requires looking at three distinct layers: its predictive brain, its digital energy grid, and its adaptive physical skeleton. In Hangzhou, municipal management is handled by a central intelligence platform known as the City Brain. This map visualization shows how data streams dictate flow. The AI processes inputs from millions of vehicles and street cameras simultaneously. By tracking these real-time variables, the system forecasts exact volumes across different intersections, adjusting signals to reroute cars and prevent bottlenecks before they form. This logic extends past transit. Suzhou connects entire factory floors into the civic network to coordinate logistics, while Chengdu utilizes digital twins to simulate urban planning decisions in real time. Harnessing this raw input shifts civic management away from damage control. The system optimizes the environment preemptively. In this model, the foundational resources of the city are data and electricity. The Sino-Singapore Tianjin Eco-City provides the physical footprint for this energy transition. This network line chart illustrates the smart grid in action. Power flows from high supply zones to high demand nodes, actively balancing based on real-time consumption. As the load balances, a bar chart records a sharp automated drop in total emissions across the megacity. Power distribution is decoupled from manual oversight. The urban operating system dynamically reroutes energy exactly where it is needed, maximizing efficiency without human intervention. A massive population density forces engineers to confront strict physical boundaries. Historically, mountains, valleys, and major riverways dictated the absolute limits of civic expansion. In hubs like Chongqing and Wuhan, developers bypass these natural restrictions. The terrain is treated as a logistical variable. Infrastructure, like this multi-level industrial bridge, crosses a major waterway while constantly monitoring its own structural integrity through embedded sensors. Transit networks intersect directly with residential spaces, routing trains straight through the centers of high-rise apartment buildings. Physical space yields to the requirements of the grid. The infrastructure adapts completely to both the geographical landscape and the demands of the digital network. This level of integration forces a re-evaluation of architectural design itself. In Guangzhou, the Canton Tower operates as a massive vertical platform for sensors and computers, feeding environmental data directly into the city's central intelligence. These structures provide the physical hardware for the network nodes that sustain the surrounding city. The distinction between a concrete building and a digital sensor no longer exists. They form a single, unified sensory environment. Zoom out to a major hub like Shanghai, and the scale of these concurrent operations becomes visible. High-speed maglev lines physically link these independent smart zones together into one cohesive regional system. None of this is theoretical planning. Millions of commuters rely on these exact pathways and automated gates every single day. This model for a data-driven megacity has moved out of the testing phase. While other regions debate how to integrate these systems, China has already made them a reality. Why have the wealthiest metropolises on Earth fallen so far behind the curve? It isn't a lack of money or technical skill. Cities like New York and London control trillions of dollars in capital and house some of the world's most capable engineering minds. The bottleneck is the process itself. Western development is often paralyzed by fragmented planning, decades-long approval loops, and construction costs that inflate before work even begins. We tend to build reactively, trying to wedge new train lines into ancient, crowded neighborhoods. China builds proactively, designing the entire transit ecosystem first and then growing the city around it. You can see the result of that planning in spaces like the Daxing Airport. The geometry of these hubs is engineered specifically to manage a high-velocity throughput of millions of passengers without creating choke points. The widening gap is the result of a system optimized for rapid, large-scale execution, competing against one bogged down in its own complexity. In practice, this means the physical structures and the digital networks operate as a single integrated unit. A massive high-speed rail network acts as the physical spine. It binds distant clusters together, moving an immense labor force across hundreds of miles in a matter of hours. Once that workforce enters the city limits, a secondary layer of sustainable transit takes over. Fleets of electric buses manage the localized last-mile distribution with minimal noise or emissions. Managing this volume of movement requires a city brain, a centralized artificial intelligence platform that monitors the entire metropolitan grid in real time. By analyzing millions of data points from cameras and sensors, the system spots congestion as it forms. It can automatically adjust traffic signals and transit routes to clear a bottleneck before humans even notice a delay. Linking physical transit to this centralized brain creates a reactive network that shifts its own infrastructure to accommodate the immediate needs of the population. At the upper limits of this ecosystem, magnetic levitation trains glide friction-free over elevated tracks, pushing the boundaries of urban transit speed. This automation extends to global logistics as well. Massive shipping ports now operate with automated cranes and driverless trucks, orchestrating the flow of global cargo around the clock. For the individual citizen, the experience is designed to be frictionless. Physical tickets and cards are being replaced by immediate facial recognition, allowing commuters to pass through turnstiles without breaking their stride. By removing the physical and digital friction points that define 20th century life, these systems maximize the city's most valuable resource, time. These cities face significant real-world challenges, from economic headwinds to demographic shifts, but their baseline operational hardware is generations ahead. The end result is a continuous 24-hour vibrancy, an incredible level of efficiency that was entirely theoretical just 2 decades ago. While planners in the West continue to debate what the urbanization of the future might look like, China has already built it. If this is the operational blueprint of 2050, then what era are the rest of us currently inhabiting?